Assalamu alaikum everyone. This is lecture number 28 of Signal and Systems course, and I'm your instructor Muhammad Rizwan Azam. So in the last lecture you have gone through the concept of the Laplace transforms, and you have seen that the convergence condition for Laplace transform can be defined by this equation. We can see that this equation is similar to the Fourier transform convergence condition, but we have an extra e raised to the power minus sigma t here. So this tells us that the convergence condition for Laplace transform also depends on the sigma, which is the real part of the S. So from here we defined the concept of region of convergence for Laplace transforms, and we saw that the region of convergence is defined by those values of S, or in this case real of S, for which this integration converges. We have also seen that the Laplace transform expression x of S is not unique. So two or many signals can have the same Laplace transform expression. So to completely characterize the Laplace transform, we require the algebraic expression as well as the region of convergence. So in this lecture, we will explore some specific constraints or properties on ROC for various kind of signals. So if we know these properties, we can directly know the ROC from the expression of x of S and some other characteristics of the signal. So let's start with the property number 1. The property number 1 states that the ROC of x of S consists of strips parallel to the j omega axis in the S plane. So we have already seen that the convergence only depends on the real part of S, which is sigma. So that's why if we see the S plane, this is the real part and this is the imaginary part of the S plane, and if we fix this point, let's suppose, as sigma, then this will define this whole vertical line. So what does that mean? That the region of convergence will be either on this side or on this side. So this will define the strip which is parallel to the j omega. The property number 2 states that for rational Laplace transforms, the ROC does not contain any poles. We have already seen the definition of the pole. So let's suppose x of S is n of S divided by d of S. Then poles will be those values of x of S where d of S goes 0 and x of S goes to infinity. So when the x of S goes to infinity, it means that in the convergence condition, this integration is not converging. So it means that at a pole, the integration does not converge, and hence that point cannot be in the region of convergence. So that's why we're saying that the region of convergence should not contain any poles. So number 3 property states that if x of t is of finite duration, means if it is in between two times, let's suppose t1 and t2, and 0 otherwise, there's no value of x of t here, and we have another information that it's absolutely integrable in this range, then the ROC is the entire S plane. So to verify this property, let's suppose x of t is the signal, and we multiply e raised to power minus sigma t with this signal. If sigma is positive, the product will be decaying and the product will be of this type. And similarly, if sigma is negative, then the exponential will be growing and the product will be of this type. So in both the cases, we can see that if the original signal x of t is not diverging, then their product is also not diverging. So mathematically we can prove this as if x of t is absolutely integrable, that means that this integration is converging to a finite value. Then let's suppose we take sigma positive. So if we take sigma positive, we can see from here that the maximum value this product can get is on the time t1. So we can say that for any value of sigma, this integration will be bounded by the maximum value at time t1. So if the right hand side is bounded, then the left side will also be bounded. So it means that for greater values of sigmas, we can take any values and the integration will converge. So that means that ROC will be the entire right half plane. And similarly, if we take the negative values of sigma, we can also see from here that for negative values of sigma, the maximum value we can get is at T2. So it means that we can say that this integration is bounded by the maximum value here. And from here we can see that the ROC will be entire left half plane. So if we see them together, we can say that the ROC in the entire S plane. So as this property 3 stated. So once again, if x of t is a finite duration, then the ROC will be entire S plane. So let's do an example. Let's suppose we have x of t. The x of t is a finite duration from 0 to t. Then the Laplace transform of x of t will be x of s e raised to power minus at e raised to power minus st. Let's suppose we have this expression, we can write it as 0 to t e raised to power minus a plus s into t, and if we take integration, this will be just minus 1 over a plus s multiplied with the e raised to power minus a plus s, and the limits are t and 0. So if we apply the upper and lower limits, we will get e raised to the power, there is a t here, so e raised to the power minus a plus s into t minus, when we apply 0 it will be 1. So if we multiply minus 1, then we will get 1 over a plus s 1 minus e raised to the power minus a plus s capital T, which is the same expression here. From here we can see that this is a finite time signal, and from the property 3 we can say that its region of convergence is the entire S plane. But if we see here, it appears that there is a pole at s equals to minus a, and we have seen from property number 2 that this pole s equals to minus a cannot be on the region of convergence. So what does that mean? That means that property 2 and the property 3 are conflicting. They have conflicting requirements. So let's see. So at s equals to minus a, what is the value of x of s? We can use L'Hopital rule, because if we put s equals to minus a here, the denominator will be 0 and the numerator will be 0 as well. So we have to apply the L'Hopital rule. So at s approaches to minus a limits, if we take derivative of the numerator and the denominator as well, the denominator will be 1. So if we differentiate this part, d by ds is minus e raised to the power minus s plus a into capital T. We can separate e raised to the power minus s, and the bracket is here. So we can separate these two terms. These are minus e raised to the power minus s capital T into the e raised to the power minus a capital T. So this term is constant, we can take it out, and then we will be left with the e raised to the power minus a capital T multiplied with the differential of e raised to the power, or we can take this minus sign out here. So e raised to the power minus s capital T. So from here, minus t, minus minus cancelled, t into e raised to power minus a capital T into the derivative of this will be e raised to the power minus st. So if you see here, we have the same expression. If we apply the limits, then we can see that we will be left with the x of minus a, which is t. But we have seen that if we evaluate x of s at s equals to the pole, the x of s should be infinity, but this is not the case here. So what does that mean? That means that x s equals to minus a is not a pole. Okay, so this is not a pole of this x of s. That's why we don't have any conflicting requirements. The this system x of t, or we can say that its Laplace transform will have the entire S-plane as the region of convergence. Now let's move to the next property, which is property number 4. If we take x of t to be a right-sided signal, which means that the signal will be defined after some specific time, let's suppose t1 here, and its value will be 0 prior to this time, and there exists a sigma naught, which is the region of convergence. All the values of s for which sigma is greater than sigma naught will also be in the region of convergence. So let's explore this concept here. So let's suppose sigma naught is its region of convergence. Then we can see that the convergence condition can be written as this. So let's see, we have another sigma 1 which is greater than sigma naught. Then we can see that their exponential will be converging faster. So what does that mean? That means that this condition will also be fulfilled, even it will be finite, and it will be converging faster. So what does that mean? That means that for all the values which are greater than sigma naught, this integration will be converging, and all the sigmas which are greater than sigma naught will be in the region of convergence. So that's why we have said that any sigma which is greater than sigma naught will be on the ROC. And similarly, for the left-sided sequences, the argument is same, and we can say that if sigma naught is on the ROC, then all the values of s for which sigma is less than sigma naught will also be on the region of convergence. So what do we say? We are saying that let's suppose this is the S-plane and this is sigma naught for a left-sided sequence, then this whole plane will be in the ROC. Okay, and similar is the case for above property as well. So let's move to another type of signal, which are the two-sided sequences or two-sided signals. Two-sided signals extend to either side of the time greater than 0 and time less than 0 as well. So if we want to explore this property, we can represent this two-sided signal as the combination of two right-sided and the left-sided sequences. What do I mean by this? We can write x of t as the combination of xr of t and the xl of t. Then we can find the region of convergence of x of t, which will be the common area of xr and x of l. We can see from here that let's suppose this is the region of convergence for the right-sided sequence or signal, and if we have the region of convergence for the left-sided signal as this, then the common region between them will be the region of convergence for x of t. So let's do an example. So let's suppose we have a signal e raised to the power minus bt. So for both values of b, the signal is plotted here. For positive value of b, the signal will be consisting of decaying exponentials, and due to this t mod, it will be symmetric on both the sides of the time. And if we see b greater than 0, then this signal will be diverging on both of the sides. Okay. So if we want to find the Laplace transform of this x of t, because this is a two-sided signal, we can see that it is extending on the both sides of the time. Then we can divide this signal into sum of a right-sided and the left-sided signal. The right-sided signal can be represented by this expression, and the left-sided signal can be represented by this signal. So from previous examples 9.1 and 9.2, we already know that for e raised to power minus bt ut, you will get this Laplace transform, and the region of convergence for this term will be greater than minus p. And similarly for the other part, we will get this Laplace transform, and the region of convergence will be less than plus p. So now let's suppose if b is greater than 0, because if b is less than or equal to 0, there will be no common region, hence the Laplace transform for x of t will not exist. So we will take the part where the Laplace transform exists. For that, we have taken b greater than 0, and the Laplace transform of this will be, let's see it here. So let's suppose e raised to the power minus b t mod, its Laplace transform is, let's suppose 1 over s plus p, we have seen from here, and minus 1 over s minus p. So let's suppose we have its Laplace transform, so we can easily take s plus p multiplied by s minus p, and we will get s minus p minus s minus p here. So we will be left with the minus 2b divided by s square minus p square, that we can see from here. This is the same, and the region of convergence of these two will be the common portion. We can see from here, let's suppose we draw it here, this is the minus p, and let's suppose we draw the region of convergence. So the region of convergence of this will be on this side, and if we take, let's suppose this is minus b and this is plus b, its region of convergence will be on this side. So the common area is this one. So that's why we have taken this common area as the region of convergence for x of t. Okay. Then there are some other properties which are actually derived from the previous properties. The property 7 states that if the Laplace transform x of s of x of t is rational, then the region of convergence is bounded by poles or extends to infinity. We have seen this many times, that if there is a pole, let's suppose x of s is 1 over s plus 1, then the region of convergence will be bounded by, so this is the point, let's suppose, then the region of convergence will be either on this side or on this side, depending upon the conditions and the type of the signal. Then the region of convergence will be bounded by the pole itself. The pole will not be on the region of convergence, but the region of convergence will be bounded by this pole. And the property number 8 states that if the Laplace transform x of s is rational, then if x of t is right-sided, the ROC is the region in the s-plane to the right of the rightmost pole. We have already seen that, and let's suppose we have x of s as 1 over s plus 2, 1 over s plus 3. Then we have the the pole 0 map as, if there is a pole, there is a pole, and let's suppose it's a right sided sequence, then the region of convergence will be on this side, okay, because this is the rightmost pole. And similarly, if x of t was the left sided signal, then the region of convergence would have been on the left side, so this would have been the region of convergence. We can explore this property some more in the next example. So let's suppose we have the Laplace transform of some signal as expressed by this expression. So there are basically 3 possible region of convergences that can be associated with this expression. This is minus 1, this is minus 2. These are 2 poles at the pole 0 plane. So let's suppose we have a right-sided signal, then the region of convergence will be on this side, and let's suppose we have the left-sided signal, then the region of convergence will be on this side, and if we have the two-sided signal, then the region of convergence will be some area which is common to both. So these were the 8 properties which are associated with the region of convergence, and if we know these properties, we can easily find the region of convergence from directly the expression of x of s, and if we also know the time domain characteristics of x of t, then we can easily know about the region of convergence of that signal. So let's move to the second portion of this lecture, which is the inverse Laplace transform. So we have already seen that the Laplace transform of general signal x of t is defined by this equation, and we have seen that this equation is actually the generalization of Fourier transform for s equals to sigma plus j omega. In this Fourier transform, this sigma was 0. So for s equals to sigma plus j omega, the Laplace transform equation will be this. We can see from here that this is the exact same Fourier transform equation with x of t now replaced by x of t e raised to the power minus sigma t. So we can invert this relationship by using the inverse Fourier transform equation, which was 1 over 2 pi x of j omega e raised to the power j omega t. So now we replace x of j omega by x of sigma plus j omega. From here, if we multiply e raised to the power sigma t on the both sides, we can get x of t as this. So what does that mean? That means that to recover the x of t from its Laplace transform evaluated at a different values of s, where sigma is a constant value and omega ranges from minus infinity to infinity. So we can replace this information into this expression. So let's suppose we change the variables from omega to s, and similarly let's suppose we have ds which is equal to d sigma plus j omega. We know that sigma is constant, then we will have ds equals to d j omega, or we can say that d omega equals to ds by j. So we have replaced omega by s and d omega by ds by j in this expression. So from here we got the following inverse Laplace transform expression. So this expression says that if we know the x of s, the Laplace transform of x of t, then we can revert back to its time domain signal x of t. And also we have seen that since sigma is constant and the omega is varying from minus infinity to infinity, so the contour of integration is a line. Let's suppose if we plot it here, the contour of the integration will be a vertical line which extends from minus infinity to infinity on the j omega axis, and the sigma is constant, so which gives you this limits of this integration. However, we will not go into much detail of this expression. This was just to tell you how the inverse transform expression is found. Generally, when we have to find the inverse Laplace, we use the partial fraction extension technique. So let's suppose we have the expression for x of s, and we have assumed that there are no multiple poles for x of s. We have assumed that x of s, let's suppose it contains some zeros and some poles, and we have said that these poles are not repeating, they are not multiple ordered, and similarly we have assumed that the order of poles is greater than the zeros. Then from the partial fraction expansion we can express this x of s as this expression where m defines the number of poles and this ai is constant. We can find the values of this capital A and the other coefficients associated with the pole number I by using the partial fraction expansion technique. So if we know the ROC of x of s, from here we can find the region of convergence for individual terms. So let's suppose the ROC of any term s equals to minus a is on the right side of minus a. What does that mean? That means let's suppose we have a term here and its region of convergence is on the right side. So we know that this will be a right-sided sequence, and from example 9.1 we understand that the inverse Laplace of 1 over s plus a term will be ai into e raised to the power minus ai t. And similarly, if some ai, some pole, has the region of convergence on the left side, then what do we know about this ai, this pole? That this pole corresponds to a term which is a left-sided signal. So the Laplace transform of this can be found from the example as we found in the example 9.2. This will be ai into e raised to the power minus ai t multiplied with u of minus t. You can multiply u of t here as well. So now let's move to the example. Let's suppose we have this expression for x of s, and we know the region of convergence in this case is real of s is greater than minus 1, means sigma is greater than minus 1. So if we plot the converge, region of convergence for x of s, this will be, actually we have two poles, one at -1 and the other at -2, and the region of convergence of capital X of s is here. So firstly we have to find the partial fraction expansion, and then we will find the region of convergence for individual terms. We know that X of s can be written as a divided by s plus 1 plus b divided by s plus 2. This X of s is, by the way, 1 over s plus 1 s plus 2. So we can find a by just multiplying the associated term s plus 1 on the left side, 1 over s plus 1 s plus 2 multiplied with s plus 1, and we will put s equals to -1 here. So the s plus 1 term cancels out and we will get a as 1 over s plus 2 when s is equal to -1. So if we put s equals to -1 here, we will get 1 divided by 1. So a is 1. Again, from this expression we can find b as b is 1 over, when we multiply s plus 2 on the left side, we will get just 1 over s plus 1, and we will take s equals to -2 here. So if we take s -2, we will get 1 over -1, so we can say b equals to -1. So we know this information. Now we can write this partial fraction expansion, this form, by putting the values of a and b. Now we have X of s equals to 1 over s plus 1, and b was -1, so 1 over s plus 2. So now we know that X of s is, contains two terms, or we can say two signals. We have to find the individual ROC. So let's suppose this is the first term associated with this pole -1, and this is the second term associated with the pole at -2. So if we see the original region of convergence, this was right to the -1 pole. So what does that mean? That means that the region of convergence of these two should be on the right side, firstly, and secondly, the common part of both will determine the region of convergence of X of s. So there's no problem with this pole. This is exactly the same region of convergence as was in the case of X of s. Now for this pole -2, we can see that if we extend the same region of convergence so that it is bounded by a pole, we can extend the previous region of convergence by -2 pole. So we can write this as region of convergence as this. So what does that mean? The term associated with -1 pole has the region of convergence as the real part of s is greater than -1, and the region of convergence of this term is real of s is greater than -2. And we can see that the common part of this is again the same as the region of convergence for X of s drawn here. Okay, so now we have understood that both of these signals are a right-sided signal, as we have seen that if it is bounded by a pole and extends to the right side, then this is a right-sided signal. So for the first term, 1 over s plus 1, we know this is a right-sided signal. So from example 9.1, we can see that inverse Laplace transform of 1 over s plus 1 was e raised to the power minus t, because a is 1 here, into u of t. And for the second component, 1 over s plus 2, the Laplace transform or inverse Laplace transform is just e raised to the power minus 2t into u of t. And we can write the region of convergence of each term here as well. The region of convergence for the first term was real of s was greater than -1, and the region of convergence was, for this term, was greater than minus 2. So if we write these terms combined, we can find the x of t of this partial fraction expansion as simply e raised to the power minus t minus the second term, so minus e raised to the power minus 2 t into u of t, which is actually the Laplace inverse of 1 over s plus 1 s plus 2, which is x of s, and the region of convergence for x of s was, real of s was greater than minus 1. So in this example we have seen that if we have this kind of x of s, which is 1 over s plus 1 into s plus 2, and we have the region of convergence defined by a is greater than minus 1, then we will get x of t as this value. Now let's suppose the region of convergence for the above example is changed. Now the region of convergence is the real of s is less than minus 2. So what does that mean? That means that this is minus 1, this is minus 2 pole again, and the region of convergence will be less than minus 2 here on this left side. So from here we can find that for the pole at minus 2, the region of convergence will be same, and for the pole at minus 1, we can easily extend this this region of convergence to the minus 1 part. Now its region of convergence will be this. So we can again verify that the common part of these two is again the same. So the region of convergence of the first term, or the term associated with minus 2, is real of s is less than minus 2, and the region of convergence of the second term is real of s, we should write it as real of s is less than minus 1. So from this region of convergence we can see that the first term is the left sided signal and also the second term. Okay, so let me write the terms again. So x of s was 1 over s plus 1 minus 1 over s plus 2. So now we know that these two terms are for the signals which are left sided signals. And from example 9.2 we know that for a signal which is left sided, its Laplace, inverse Laplace, can be written as minus e raised to the power minus at, a is 1 here, minus t into u of minus t. And the region of convergence for this term is real of s was less than minus 1. And similarly for the next term, which is 1 over s plus 2, we can define the Laplace inverse as e raised to the power minus 2t into u of minus t. And the region of convergence in this case was less than minus 2. So if we combine these two, we can get the final x of t, which is minus e raised to the power minus t, and this minus and the minus here cancels out, so we will get a positive sign here, e raised to the power minus 2t, and if we take u of t common, minus t common, then this is the inverse Laplace transform for 1 over s plus 1 and 1 over s plus 2, and the region of convergence in this case is real of s is less than minus 2. So we have seen that for different region of convergences, the same x of s will give you the different x of t, and we can apply another region of convergence on the same signal as if we have region of convergence for above x of s as, let's suppose, real of s is greater than minus 2 and less than minus 1. So the region of convergence for x of s is defined as, this is minus 2, this is minus 1, and the region of convergence will be defined by this portion. So what does that mean? That means that the pole at -2 is a right-sided signal and the pole at -1 is a left-sided signal, and the common portion of these two signals is defined by the region of convergence of x of s. So I'll directly write down the x of t signal, which will be for the -1 term, we will get, it is a left-sided signal, so we will get minus e raised to the power minus t u of minus t, and for the next term we will get it is a right-sided signal, so we'll get e raised to the power minus 2t into u of t. So this whole term is actually x of t, and this is the inverse Laplace transform of the same x of s as we have seen earlier for the case when the region of convergence is in between -1 and -2. So from all of these examples we can see that we can convert back x of s into x of t, and we have also seen that for the same x of s, for various regions of convergence, we will get different x of t. So that's all from my side in this lecture. We will meet in the next lecture.